Good morning. I would invite Deepashri ma'am to start the session.
So my screen is visible. Okay. So yesterday
Yes,
we
ma'am.
okay. So yesterday we dealt with ideal gas undergoing any process and their delta H calculation. So basically we did the delta H calculation for any kind of physical processes, right? So today we will be dealing with the delta H for any kind of chemical process. So let's start. So today we are going to dealing with the calculation of the delta H for any chemical process. Okay. So suppose reactant is converted to product. Okay. And volume and temperature there is change. So here for this condition QV will be equals to delta U. And R is converted to P. So here what will happen? P and T are changing. So here QP is equal to delta H. These are the two different conditions. Okay, now case one. What is case one? If only gaseous reactants, if only gaseous reactants and products are present, then uh, so we have assumed here that all gases are ideal. Okay, so what we have assumed? We assumed here that all gases are ideal. Okay, so if this is the case, then we get a formula. Delta H is equals to delta U plus again, this is another formula that might come in your exam. Okay, so this is one of the important formula that might come in your exam. This is, you just have to remember to need the formula. What is Ng? Ng is the moles of the gaseous product minus moles of gaseous reactant. Is this part clear? Moles of the gaseous product minus the moles of the gaseous reactant, and we get this kind of formula. You have to remember what? We have to just remember this formula. Now, case 2. What is the case 2? Case 2 is if along with the gases, solid liquids are also present. If along with the gases, solids and liquids are also present. Okay. So what will be the case here? Let's just write a equation. Now, this is the equation. So due to presence of solids, due to presence of solids and liquids, what we get? Delta of PV is equivalent to 0. So we know the general equation as delta H is equal to delta V plus delta of Ng RT. This is the general equation, right? We have just learned. Here delta Ng will be this D minus this A, because only these two are gaseous, rest nothing is gaseous. Only you have to subtract the moles which are of gaseous. Only A and D are gaseous. So it will be D minus A. Before reactant first, then, product first and then the reactant side. Okay, this is the rule. This is the rule. This is the first the product side, then the reactant side. Minus reactant side. Okay, this is the general rule. Okay. Now, once we get this, then we can do this formula. Like this formula remains the same. Ultimately, like delta H is equals to delta V plus D minus A RT. If this is the equation. Okay, so is this formula clear? If you have, like if in your exam, the question has asked you to calculate the delta H for any liquid, then that formula works. If they ask you to calculate the delta H in an equation where both solids and liquids are present, you have to use this formula. R will be given, T will be given, volume will be given. This equation you can see from your question, and thus you can calculate. So just search for these keywords. Whatever they are asking, accordingly use that kind of formulas only. Okay, so this is something I'm doing for boards. One important derivation I left off for boards. Work done during a chemical reaction. Okay, so what is this? A of gas plus B is also in the gaseous state. We have considered volume and temperature to be variable, and we are getting 4C. Suppose it is gaseous. Here W is equals to 0. Again, A is gaseous plus B is gaseous, and here P and T are varying. So here also we get 4C, which is gaseous. So, but here the work done will be So this is your standard formula and its derivation. Okay, so this might come on your exam, this might not come for your exam, just to make you, if they ask you in your exam, if you can solve, they can so that you can solve, I have given this. Now can anyone explain me this derivation, what I have done and why I have done? Anyone can explain me the derivation? No one. See here, let me explain it. Here we are calculating the work done for a chemical reaction. What is the chemical reaction? Our general chemical reaction is a gas reacting with another gas and producing 4C. Okay, this is another gas. Okay, so what I have told you yesterday, what is the general formula for work done? This is the general formula for work done. Okay, so W is the work done, P is the external pressure, dV is the change in volume. So I have started the derivation by assuming that the reaction takes place at a constant temperature and pressure. Okay, at a constant temperature and pressure. Under these conditions, the ideal gas law can be used. At constant temperature plus pressure, ideal gas law can be used. Okay, to relate the volume of the gases with the number of moles. Wait, let me write this. Used to relate to relate what? Volume of the gases. Volume of gas with number of moles. That is PV is equals to nRT. So I have considered pressure and temperature constant, and at this condition, at constant temperature and pressure, ideal gas law can be used. So if we differentiate both sides, I'm doing it in the next page. What is the formula? What I've told you, that at this condition, I can use this formula. Now, if I differentiate both sides, I'm writing, differentiating both sides with respect to volume. Just trust me, if I differentiate this equation with respect to volume, I will get PdV plus VdP is equal to nR dt. nR is the constant. Since temperature is constant here, in the equation I told pressure and temperature is constant. Temperature is constant, so dt will equivalent to 0. Therefore, our symbol, so what will happen? PdV plus VdP is equal to nR into 0 is equal to 0. So PdV plus VdP is equivalent to 0. So PdV is equals to minus VdP. Is this part clear now? Up to this? Is this part clear? Up to this, whatever I have written? We start off with an equation where pressure and temperature is constant. And I told you at this constant, we can use this equation. Then I differentiated this equation with respect to volume. And now I have got this. I have got this expression. Up to this, is it clear to everyone? Yes or no?
Ma'am, can you explain once again?
Okay, explaining once again. Suppose this is a chemical. What I have told, we have to calculate the work done during a chemical reaction. What is chemical reaction? This is our chemical reaction. A plus B producing 4C. All are in gas. And what is the general formula for work done? Minus of integration PD. Is this part clear still now?
Yes, ma'am.
Till now clear? Now, suppose at a constant, now if this reaction, this chemical reaction is occurring at a constant pressure and temperature. Okay, suppose. Now, why I have considered constant pressure and temperature? Because if the pressure and temperature is constant, then we can use the ideal gas equation, which is PV is equal to nRT. Is this part clear?
Yes, ma'am.
Good. So
Ma'am.
after using the ideal gas equation, what I have found? PV is equal to nRT. Now, since you don't know about the differentiation process, hence I have done the differentiation here. Okay, so this is the differentiation process, that PDV plus VDP. Wait. So PDV plus VDP is equal to NR dt. See, NR is constant, okay? NR T though. So here T is only variable. So NR is the general constant. So we get the equation like this. But for our question, we know temperature is constant because I have considered pressure and temperature to be constant. So our dt becomes constant too. Okay. So if something is constant, then it becomes zero. Then that derivative becomes zero. It is the rule of derivative. If anything is constant, then it becomes zero. Is this part clear? So far?
Yes, ma'am.
Good. So I have written the same equation as this. NR into 0, which is 0. PDV plus VDP is 0. So we have got till now. Now is it clear? Yes or no?
Yes, ma'am.
Good. Now, this is the general formula for work done. This is the general formula for work done. Yes or no? Work done, we know this is the general formula for work done. Work done is minus of integration PDV.
PD.
Yeah? Okay. Now, asterisk. Work done is minus of integration PD. This is our general formula. Now, can I write like this? Can I write like this? I have replaced PDV by VDP.
Yes, ma'am.
Replacing values of PDV. So what do I get? Minus minus gets plus, integration of VDP. Okay. So this integral, what color should I choose? So this integral can be evaluated by using the limits of integration. Now, what is our so far what we have done? We have considered here. Now go back to the original equation. pressure and temperature is constant. Is the volume constant? According to our equation, pressure and temperature is constant. Is it written volume is constant for this equation? No.
No.
So volume is variable. So what will be the limits of our, what will be the different limits of our integral? So the
V1
limit
and V2.
of our integral will be V1 and V2.
V2.
Okay. Which represents the initial, V1 is the initial volume, V2 is the final volume. Done. Okay, so this will be our integral. So if we solve, it will come as P into V2 minus of V1. After integration, we will get this. After integration. Okay. So now we can substitute the ideal gas law in the given equation. Yes or no?
Yes, ma'am.
Now substituting ideal gas law into the equation. W is equals to nRT. V2 minus V1. Okay, V2 by V1 minus 1. Right, goes with the same. PV is equals to nRT. We have just written the formula like this. Okay. Now, one more thing. So up to this, everything is clear? Clear or not everything till now? I've just replaced the ideal gas equation here.
Ma'am,
Yeah,
is it P equal to nRT or PV equal to nRT?
PV is equals to nRT.
Then P equal to nRT by V now, ma'am.
Okay, now you tell me why.
Ma'am, we are substituting only P value, not P and V now, ma'am.
Yeah, we are doing that. But why I have written that? Wait. Why I have written that? Just think once. Anyone else can say?
Ma'am, have you,
Wait.
divided V with V2 and V1?
Yes.
Okay, ma'am.
Okay. Understood. I guess it is clear now. So
Yeah, ma'am.
now we will be calculating the number of the moles of the gas in terms of the stoichiometry coefficient. Like A of gas plus B of gas producing 4C. So the number of moles of gas before the reaction is 2. 1 plus 1, 2. 1 mole of A, 1 mole of B. Number of moles of gas after the reaction is 4. So if we use the formula W is equals to delta nRT. So where delta N is the number of the changes of the moles, so it becomes 4 minus 2 is equals to 2. So work done is equals to minus 2 RT. Okay, this is the formula. So this is the final work done during the chemical reaction. Here. This here I have replaced with -2. Okay. So this is the derivation. This is the formula. Okay. So what I have done here, W is equals to P V2 minus V1. Up to this, I guess it is clear to everyone. Now I have replaced this V2 by P and this V1 by P. Okay, if just forget this step. What I have done here. See, what I've done here, minus P of external, I have replaced, after getting this part, I have replaced with entire V with final of N minus initial of N. So I have to write here one more thing. So from, wait, up to this part is clear. After integration, what we are getting?
Yes, ma'am.
Good. So I have just used this equation here. Minus P of external V2 minus V1. Okay. So what is V? PV is equals to nRT. So what is V? V is nRT by P. So nRT, N is the final minus divided by P, same thing, minus N of initial. So what it is coming here? If I write one more statement, minus N of final RT minus N of initial RT. This is coming. If I take RT common, N of final minus N of initial. So what is this? Delta N, RT and negative. So this will be minus delta N RT. Now is the derivation clear to everyone? Check and let me know. Is the derivation clear to everyone now? Okay, I am
No, ma'am.
summarizing.
Yes,
Huh?
ma'am. Yes,
Good.
ma'am.
I have started with this equation. At a constant pressure and temperature, I know at this constant, I can use PV is equals to nRT. Then I have simply derivated it with respect to volume. I have got this equation. Now I know dt is constant too, because dt is not constant. Dt is constant because temperature is constant. Because in our equation, we have considered to be pressure and temperature only variable. So dt becomes constant here. If dt is the constant here, it becomes 0. So we get this formula. Now we know that the general formula for work done is this. So I can have the work done formula like this, and I've just replaced this value here. Now, what is the variable? Our pressure and temperature is constant. So volume is the variable. So after integration, we get this. Now, since we know at this condition, we can use PV is equals to nRT. I'm replacing the volume with the nRT by P formula. Okay, so that is this, and we get this final formula. So for this equation, our delta N will be 4 minus 2 is equals to 2. Is this part, is the whole equation clear to everyone? Or should I repeat it once more? Is this part clear to everyone, or should I repeat it once more? Just say, or else I
Ma'am,
will start it. हाँ बोलो.
after integration, we have written W equal to nRT into V2 by V1 minus 1, ma'am. Then what about that?
Okay, I am doing this equation once more. Okay, let's just forget this. We will be solving this equation again. Okay. So this I have crossed. This I have crossed. Wait, I am solving this equation again. Okay. So what was our equation? A of gas plus B of gas will produce 4C, which is also in the gaseous state. And what I told, pressure and temperature is constant. Okay. Now you need to know at a constant, these are constant. At a constant pressure and temperature, we can use the pressure and the temperature is constant, and we under this condition we can use the ideal gas law. Ideal gas law. Ideal gas law. That is PV is equal to nR. So what is our first equation? PV is equal to nRT. Now, since you don't know differentiation, just trust me. Differentiating with respect to what I will do? With respect to volume. Okay, so we will get P dV plus V dP. This will give you nR dt. Just trust me that if I differentiate this equation, I will be getting this equation. Okay, nR is constant. We cannot differentiate the constants. Okay, we can differentiate only the variable. According to our question, to our given chemical reaction, pressure and temperature is constant. Therefore, delta T will be equivalent to 0. This is by the law of differentiation. In differentiation, anything if it is a constant becomes 0. Okay, by law of differentiation. Okay, so what will our equation look like? P dV plus V dP is equal to nR into 0 is equal to 0. So we get P dV is equal to minus of V dP. Is this part clear till now? Clear
Yes,
or
ma'am.
not? Now, what is the general definition for work done?
By W equal to minus integral P dV.
Good. I am just replacing the formula. Okay, so what we get? Integration of V.
VD.
Yeah. So what I told in the question, say pressure and temperature is variable. So pressure and temperature is constant. So our volume is variable. Volume 1, volume 2. Okay. So these, whatever is the variable becomes the limits of the integral. Okay. Is this part clear now? And after solving this integral, we will get work done is P into V2 minus of V1. Till now, is it clear?
Yes, ma'am.
Good. Now, so what we got? We finally got P is equal to P into V2 minus of V1. Now, we know we can be using this equation. We know we can use this equation. Okay. What is V2? See, volume 2. Volume 2 means N will be final, and volume 1 means N will be initial. If the equation has two parts, then you can understand V2 means the N2 and V1 is the N1. So N of final RT by P minus N of initial RT by P. Okay? If I take RT by P common from, you can take common like this. This is the common part in both the equation. Okay, so N of final minus N of initial stays. This P cancels out. N of final minus N of initial RT. This N of final and N of initial is called NG RT. So work done is delta NG RT. This is the derivation. Is the derivation clear to each and everyone now?
Yes, sir.
Okay, fine. So for our equation, what was our equation?
AG plus BG equal to 4CG.
1 mole, 4 moles. So before reaction, here 2 moles, here 4 moles. So delta Ng for this reaction will be 4 minus 2 is equals to 2. So work done will be, okay, here a negative sign will be there. Forward to add the negative sign. Wait. Negative sign should come. Oh, yeah. Okay. This becomes your final equation. Okay. Is this part clear? You will see a negative sign here after integration. I have forgotten to. Okay, after integration, you will get there a negative sign. Okay, so is the whole concept clear to everyone? I guess now, is it clear? So let's just move to calorimeter now. Okay, so let's start with calorimetry. So it's a branch of chemistry which will deal with the management of energy exchange during any physical or chemical process, because it will be carried out in a vessel called calorimeter. So that's why it is called calorimetry. So measurements are done. Yeah. So measurements are done in two conditions. At a constant volume and temperature, at constant volume or temperature, we write like and second is at a constant pressure and temperature. So we write it as this is the rule. If it's the volume or temperature, we write like this. If it's the pressure and temperature, we write like this. So at a constant volume and the temperature, this process is carried out in a closed rigid vessel. Okay, so let's first deal with this. At a constant volume and temperature. So this reaction will be carried out in a closed rigid vessel which is called bomb calorimeter. So in this process, small amount of substance will undergo combustion, and as a result, temperature which is outside the system, that will change, and the heat is exchanged at a constant volume that can be calculated. So what I said, this process is carried out in a closed rigid vessel called bomb calorimeter. Okay, so in this process, small amount of substance undergoes combustion. So temperature outside the system. Outside system, what is our system? System is the water plus calorimeter. So outside the system, here the temperature will be constant, but the temperature outside this combination, okay, will change. And if temperature changes, what will happen? Heat will exchange. Heat exchange will occur. Therefore, heat exchange will occur at constant volume. See, inside the system, volume and temperature both will be constant. Outside the system, volume will be constant, temperature will be changing. Since there is a temperature change, hence there will be heat exchange. We represent heat as Q. So what we will write? QV is equal to C del T. So this heat exchange can be calculated. Okay. Is this part clear till now? I have told you at constant volume and temperature, the heat exchange will occur as QV. Okay. So I have told you that there is a system, and inside the system there is only the heat change, and outside the system temperature is changing but volume remains constant. So outside the system, since temperature is changing, so there will be a heat exchange, and that heat exchange can be calculated using this formula. Okay, here what is QV? QV is what? Heat exchanged outside of the system at a constant volume. Okay, what is C? I'm sure you have forgotten this. Heat capacity. I've told you the definition in previous classes. Heat capacity of what? of the system. What is our system? Water plus calorimeter. Is this part clear, everyone? Is this part clear?
Yes, ma'am.
Nothing is in confusion right now?
No,
One
ma'am.
more thing. I told you here we are using bomb calorimeter. Bomb calorimeter is used where? Bomb calorimeter is generally used when gaseous components are involved. When gaseous components are involved. Okay, so this is the general thing. Is this part clear to everyone so far?
Yes, ma'am.
Just
Yes,
check
ma'am.
once. Wait, I'm showing you something. Wait. Let's see if I can draw this system. Wait for once. If I'll see later if I can draw this. Suppose this is a equation given. C of solid is carbon with oxygen gives you carbon dioxide. Okay, I think everyone know this equation. I hope everyone is well familiar with this equation.
Yes, ma'am.
Okay. So what I can write is that for this equation, delta U is equal to minus M by W QW. Now, what are these things? So, this discusses the bomb calorimeter. Like previously, we have explained a bomb calorimeter experiment, right? So, it is a device which is used to measure the heat released or absorbed during any chemical reaction at a constant volume. This much we have learned and understood. What are the different variables here? This delta U, it is the change in internal energy. Change in internal energy. Okay. M is the molar mass. Molar mass of the substance which is undergoing combustion. Undergoing combustion. And W is the mass of the substance. Okay, so this is the mass of the substance which is undergoing combustion. And what is this is the heat exchanged. You can write it as QV also. You can write this as QV also. So this is the heat exchanged. at constant volume. Okay. So the equation, this equation, that delta U is equal to minus M by W QV, this relates the change in the internal energy of the system to the heat system. So this relates with change in the internal energy of the system with respect to heat exchange. This is the main purpose of this equation. So minus M by W. What is the significance of this? So this term represents the mole of the substance per gram. Okay. This will represent moles of substance per gram. So do you know how to calculate mole mass, given mass by its molecular weight? Right. So if we suppose you need to calculate what is the molar weight of hydrogen. Suppose you have to calculate moles of hydrogen, 2 grams of hydrogen. Okay. So how do you calculate what is the given weight? Given weight is 2. What is the molar mass of hydrogen? 1. So that is 2 moles. Is this part clear? How to calculate moles? Similarly, we are doing it here. Whatever weight will, here carbon is undergoing combustion, right? So suppose I have told that 100 grams of carbon is undergoing combustion. Okay, so 100 divided by 12. 12 is the molecular weight for carbon. So 100 by 12 is M by W. So whatever mass is given in the question divided by its molar mass, that becomes your number of moles. So is the mole concept clear to everyone? Though you have learned about the mole concept in the first chapter, still, is it clear now? Okay. Yes or no? Now, QV. This QV, this is the heat exchanged at a constant volume. In our previous class, we have learned that there is an equation QV is equal to C delta T, where C is the heat capacity. Heat capacity. If you remember the definition of heat capacity, we have derived this formula. Okay. C is the heat capacity and delta T is change in temperature. Change in temperature. So this is the same QV. Whatever QV we are using here, this is the same QV. And delta U is the change in the internal energy, which is the total energy of the system. Okay, so in bomb calorimeter, see, total U represents what? Internal energy or the total energy, which is the summation of kinetic energy or the potential energy and everything. Now, in bomb calorimeter, I have told you in bomb calorimeter, volume is kept constant. If volume is kept constant, so there will be, what is the work done formula? PdV. Volume is constant. I told you the law of the differentiation. If anything is constant, that becomes 0. So P into 0 is equals to 0. So if volume is constant, work done will be equivalent to 0 in a bomb calorimeter. So the change in the internal energy is equivalent to the heat exchange. Okay, if you remember the internal energy, I have done that potential energy plus kinetic energy plus internal energy plus QV, and this is a huge equation. Now these things are getting 0. Why? I have just explained. So in our equation, delta U becomes just equivalent to QV. Is this part clear so far? What are these? What I am doing? Or are you guys just sleeping? I guess no. So if QV is positive here, if QV is positive, so what will happen? That is, heat is released. Positive means heat is released. So if QV is positive, then delta U will be negative. Okay, that means system loses okay, this I am doing in the next page. So this equation you have copied in your copy, the whole equation including this negative sign. You have copied all in your copy, this equation. Done or not?
Yes, ma'am.
Good. Now we will be doing some interpretation. So what was our equation? Our equation was delta U is equals to minus of M by W QP, right? Okay. Now we are making different interpretations. QV positive. If this is positive, then this along with this negative sign, delta U will be negative. Is this part clear? If QV is positive, why delta U is negative? Clear or not?
No, ma'am.
Bolo. See, what it is saying here, just simply see. Delta U, this is some kind of constant, ignore, is dependent on QV. How? There is an inverse relation. If QV is increasing, just imagine here, delta U is equal to, suppose QV is 1. This is some constant, and the value of the constant I have taken as 1. Okay. So, and this is A. So, are you getting the value of delta U negative? If I take QV as, if I take this to be 1, suppose this is 1, this is A. Okay. So, what we will get? Delta U is equals to minus of 1 into A. It is minus of A. So if Q is positive, we are getting delta U as negative. Is this part clear?
Yes, ma'am.
Clear? Wait. So I am deleting this part. Okay. So this is something we have to deal with now. Okay. So what is QV positive means? So QV positive means heat is released. And delta U negative means system loses internal energy. Now, in your NEET exam, if there is a statement saying heat released will be equivalent to loss of internal energy. Is this statement true or false? True or false?
True, ma'am.
Good. Very good. Because I told you that suppose QV is positive, then delta U becomes negative. Positive QV means heat is released. Delta U negative means system loses internal energy. So heat released will be equivalent to loss of internal energy, and this statement becomes true. Okay, we have learned so far. Now what if QV is negative? If QV, suppose QV is negative, QV I have considered to be minus A, and this whole system is 1. So what will I get? Minus 1 into minus A, delta U. So
Delta equal to what?
delta U will be plus A. So if QV is negative, delta U becomes
Positive.
positive. Is this part clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Good. So what is the interpretation? What is QV negative means? Heat is absorbed.
Absorption.
Heat is absorbed. And delta U positive means no loss of internal energy by system. So just the reverse of this statement is also true. Is this part clear?
Yes, ma'am.
Okay. So why is this overall equation given? Delta U is equals to minus of M by W QV. I told you this is mole per gram. Okay, right? So this equation will be used by you to calculate the change of the internal energy per mole based on the heat release. So use this equation to calculate the change in the internal energy of a system per mole based on measure of heat released. Now you can ask me, ma'am, you have been providing us with so many examples. So how to deal? If in your exam heat term is given, okay, heat term is given, and they have asked you to calculate the internal energy, use this formula. If they have given the other cases, if they have given the temperature heat capacity, then use this formula. Okay, it is simply you have to remember all the formulas and you have to see the question, what it is given. Whatever is given, accordingly use that formula. So that is the reason I am focusing mainly on formulas. So is this part clear? Next day, we will be learning about constant pressure and temperature. I told you that there are two cases, that one is a constant volume and the temperature, and the second is the constant pressure and temperature. We will be doing it in the next class. Okay. Is this part clear? Hopefully the whole class is clear to you. Okay. Yes or no?
Yes, ma'am.
Okay then. Okay, so I'm stop sharing. So, ma'am, that was from my end. Ma'am, are you there?
Students, you can join the next